So we're comparing two variances in 10.3, which in Chapter 8 we performed a hypothesis test when we used a t-test, and it depended on whether or not population variances were the same or they were different. So to determine if population variances are equal, you can perform a two-sample F test. So this is going to be different from what we've done so far. So an F test, we're using a new table. It's the F distribution table, and it's on multiple pages, but it starts on page A20. So this is a new table for you, but it starts on page A20. So we're letting sample variance 1 and sample variance 2 represent the sample variances of two different populations. So S sub 1 squared and S sub 2 squared. So remember, variance is squared, standard deviation is not. If both populations are normal and the population variances sigma 1 squared and sigma 2 squared are equal, then the sampling distribution of F equals our sample variance 1 over our sample variance 2 is an F distribution. The following properties go along with an F distribution. So it's a family of curves, each of which is determined by two types of degrees of freedom: the degree of freedom corresponding with the variance in the numerator, and the degrees of freedom corresponding with the variance in the denominator. So df sub n, df sub d. The F distribution is positively skewed, and therefore the distribution is not symmetric. The total area under the curve is 1. All values of F are greater than or equal to 0, and for all F distributions, the mean value of F is approximately equal to 1. When you have unequal variances, you want to make sure that the greater sample variance is your first one. So the first sample should be the bigger one. That's so that your numerator is greater than or equal to the variance in the denominator, because we always want that F value to be 1 or more. So if there's two different values for your sample variances, always make sure the bigger one is like your first sample. All one-tailed tests will be right-tailed, and for all two-tailed tests, you only need the right-tail critical value. So when we're finding critical values for F distributions, we want to specify the level of significance. We're going to find the degree of freedom for our numerator and the degree of freedom for our denominator, both of which we're taking the samples and subtracting 1. And then we're going to use Table 7 in Appendix B, which is page A20 in your book, to find the critical value. So when your hypothesis test is one-tailed, you're using alpha on the F table. So every page is a different alpha value. So the page that you use for your F distribution is going to be dependent on what alpha is. And then when it is a two-tailed test, you're going to cut alpha in half. So that's very much like what we did with Z tables. We had two tails and we had to cut alpha in half. So if it's two-tailed, cut alpha in half and use that value. If it's one-tailed, you just leave it as is. So in numbers 1 and 2, we're finding critical values. So find the critical F value for a right-tailed test when alpha is 0.05. Your degree of freedom for your numerator is 8, and your degree of freedom for your denominator is 20. So you're going to go to the page where alpha is 0.05, which is page A23. So when alpha is 0.05, we're on page A23. It's one-tailed, so we don't have to cut that alpha in half. Your degree of freedom for your numerator is going across the top. It's going across your columns. The degree of freedom for your denominator is going down your rows. So numerator is 8, so we're going to go over to 8. Denominator is 20, so we're going to go down to 20, which is 2.45. So that critical value is just going to be 2.45, which also means that your rejection region, I know we weren't asked for it, but your rejection region, since it's right-tailed, would be greater than 2.45. For number 2, we want to find the critical value for a two-tailed test when alpha is 0.01. So we're going to cut that alpha in half. So half of 0.01 is going to be 0.005. So we're going to go to the 0.005 page, which is A20 in your book. Degree of freedom for the numerator is 2 and the denominator is 5. So on the page alpha equals 0.005 page, we're going to go to a degree of freedom for 2 for the numerator, so over to 2 and down to 5. So that's going to give us a critical value of 18.31. And even when it's two-tailed, your rejection region is still going to be greater than whatever that critical value is, because remember, even when it's two-tailed, we want our F value to be greater than or equal to 1. So it's always going to have to be greater than whatever our rejection region is. So a two-sample F test for variances is used to compare two population variances. To perform the test, you've got 3 conditions. Sample has to be random, the sample has to be independent, and each population must have a normal distribution. So your test statistic is just your sample 1 variance divided by your sample 2 variance. Remember, whatever variance is bigger is going to be the one that is in your numerator. Degrees of freedom for both are just the sample size minus 1. So your first sample size minus 1 for the numerator degree of freedom, your second sample size minus 1 for your denominator degree of freedom. So when we're using a two-sample F test to compare the population variances, we want to verify that the samples are random and independent and the populations are normally distributed. Identify the claim and hypotheses, specify your level of significance, identify your degree of freedom for your numerator and denominator, find your critical value, find your rejection region, find your test statistic, reject or fail to reject, and then interpret in context of your original claim. So even though it's a different type of test, different table, it's still the same process. So a medical researcher claims that a specially treated intravenous solution decreases the variance of time required for nutrients to enter the bloodstream. Independent samples from each type of the solution are randomly selected and the results are in the table. At alpha equals 0.01, is there enough evidence to support the claim? So that means we go back to our more normal hypotheses here. So remember, we're talking about population variances. That's the goal. So if it's decreasing, that means your second sample, the treated sample, should be smaller. So we want our first sample to be greater than that. So even though it says it's going to decrease it, it's going to decrease it, but that means that that first sample has to be the bigger one, that second sample has to be the smaller one. So that's why it feels like our claim is backwards with these, because even though it's saying it's going to decrease it, it is, but remember, when you're determining which one's sample 1 and which one's sample 2, sample 1 has to be the bigger one. So if sample 1's the bigger one and sample 2's the smaller one, then sample 1 has to be greater than sample 2 for it to decrease. So when we find our degree of freedom, so degree of freedom for the numerator is going to be 25 minus 1, or 24. Degree of freedom for the denominator, 20 minus 1, which is 19. So We have a one-tailed test at alpha equals 0.01. So we're going to the page at point where alpha is 0.01, which is page A21. We're going over to 24 in the degree of freedom for our numerator and 19 for the denominator, which is 2.92. So critical value 2.92, which means that rejection region is going to be greater than 2.92. So when we find our test statistic, this might be the easiest test statistic we've done all year because it's your first sample variance, which is 180, divided by your second sample variance, which is 56. And when we divide that, we get about 3.21. So we're comparing that to our rejection region. So is 3.2 greater than is 3.21 greater than 2.92? Yes. So we can reject HO, which means we have enough evidence to support our claim that a specially treated intravenous solution decreases the variance of time required for nutrients to enter the bloodstream. So with these, really, the hardest part is making sure you're looking at the right critical value on the right table and interpreting. Once you have the critical value and rejection region, the test statistic is the easiest one you've ever found. So you're just dividing the two numbers, and then you've got to be able to interpret in context. So I would encourage you to try number 4 on your own and determine what your critical value is, all of that, so that you can perform your hypothesis test. One thing to remember is that in number 4, you are given S, which would be your standard deviation. So you have to find that variance. Remember, variance is squared, standard deviation is not. So all you're doing is taking that number for standard deviation and squaring it. Once you square it, those are the two numbers that you're going to use for your test statistic. So a biologist claims that the pH levels of the soil in 2 geographic locations have equal standard deviations. Independent samples from each location are randomly selected. The results are in the table. At alpha equals 0.01, is there enough evidence to reject the claim? So they're saying that it's going to have equal standard deviations, which means if it has equal standard deviations, it's going to have equal variances. So we need them to either be the same or not be the same. So our claim is that they're equal, which would be HO. So before I do anything else, I'm going to find what my variances are going to be. So I'm going to square both of the standard deviations. So 0.95 squared is 0.9025. 0.78 squared is 0.6084. So remember, you want your bigger variance to be your sample 1. So sample 1 is location A, sample 2 is location B. So my degree of freedom for my numerator is going to be 16 minus 1, or 15. My degree of freedom for my denominator is going to be 22 minus 1, or 21. It's an equal to, not equal to, which means it is two-tailed. So I have to cut alpha in half. So instead of 0.01, I'm using 0.005. So my critical value, I'm going to go to the 0.05 table. I'm going to go over to 15 and down to 21, which is going to give me 3.43. And I still want to be greater than that because we always write that test statistic with the bigger variance in the numerator. So when I find my test statistic, 0.9025 over 0.6084, which gives me about 1.48, which is not greater than 3.43. So I can reject HO, which means there is not enough evidence to reject the claim that pH levels of the soil at locations A and B have equal standard deviations. So always just make sure you're interpreting in context. Always make sure your bigger variance is in the numerator. If you do those two things, you really can't mess these problems up. The worst part of it is the amount of tables. If you need me, email me, text me, Google Meet, all that. Your homework, page 555, 2 through 26 even.